The twist drill is one of the most efficient tools used in the shop. Holes drilled with twist drills in proper condition and properly used can be accurate within certain limitations. However, a drilled hole may be too rough for high precision requirements. The commonest method achieving better finish and greater accuracy of size or location is by reaming. The reamed hole, therefore, permits working to the close tolerances required in precision work. Reaming practices vary from shop to shop. An operator, however, should be familiar with all the various kinds of reamers. There are many types of reamers. Exactly what type shall be used for a particular job is dependent on the method to be used and the personal preference of the user. First, there's this group, the standard production reamers. One of the common standard production tools is the straight flute chucking reamer, made with either a straight shank or taper shank. A great many users prefer the spiral fluted reamer. It is also made with either a straight shank or taper shank. The expansion reamer has been developed to reduce reaming costs in the shop. It is easily expanded to a variety of sizes by means of an expansion pin. Standard hex-type set screw wrenches are used in the expansion pin. Reamers usually are discarded because of loss of size long before they have been resharpened to the full usable flute length. This results in increased tool costs, which, however, can be reduced or avoided. The expansion reamer is designed to eliminate the necessity for scrapping such tools. Instead of throwing the reamer away when it is worn too much, the tool room attendant merely expands the blades to the original size. The expansion reamer may be expanded for resharpening to its original serviceable condition many times, thus making it an ideal low-cost, high-production tool. In production reaming operations requiring the use of an expansion reamer, an oversized hole condition is sometimes obtained. In attempting to correct this condition, however, it is a mistake to loosen the pin and attempt to ream a hole smaller in size than the original size of the reamer. This loosening of the pin removes some of the original pressure put on the cutting edges and permits the reamer to collapse, either of its own accord or under the pressure of the cut. As a result, the reamer becomes smaller in diameter at the cutting end than at the back end of the flute. This causes the reamer to wedge in the hole and break. Properly used, however, the expansion reamer is an efficient, economical tool. Another type capable of expansion is the adjustable reamer. This tool has removable cutting blades. They are locked in position in an alloy steel body by socket head blade locking screws. It is capable of expansion because of its tapered blades, which fit into tapered slots in the body. It can be adjusted to a large variety of hole sizes without regrinding. To expand the reamer, first the blades are moved forward by turning the adjusting nut. They are then locked in place by tightening the blade screws. Finally, they are securely located by tightening the locking nut. When the blades are worn out, they can be replaced with a new set. This type of reamer is used for the machine reaming of tapered holes, particularly the reaming of through tapered holes. Its high angle of spiral throws the chips ahead of the reamer. Because of this cutting characteristic, chips do not tend to pack in the flute, thus eliminating the possibility of breaking. In order to avoid waste of the entire tool, most of the solid reamers that we have seen are also made in the shell type in the larger sizes for those who prefer them. For example, here is a shell reamer with straight flute. And here is one with spiral flute. Then there is one made by brazing hardened high-speed blades in an alloy steel body. The expansion type. And the adjustable type. The shell reamer is a separate replaceable unit. When the tool is worn, just the reamer part is replaced, and not the complete tool. When replacing, it is important that the reamer and arbor be thoroughly cleaned. They both also should be checked carefully for nicks and burrs. When assembling, it should be tapped on the arbor very lightly with a soft hammer. Bridge and car reamers have been developed for reaming out holes before riveting and bolting. These reamers are made with straight flutes or spiral flutes and in long or short length. The small point enables these reamers to enter holes that overlap. Bridge reamers are designed for rigorous application. For example, the lining up of holes in structural iron and steel. Reaming holes with a car reamer likewise lines them up and opens them to a size that permits insertion of a rivet. Although this tool is called a drill, a core drill, it is essentially a reamer. The core drill is used to enlarge a cast hole, a punched hole, or a drilled hole, where the accuracy and finish requirements are not too great. For example, it has the advantage of being able to remove considerable stock from a cored hole. This cutting ability of the core drill often eliminates the necessity of drilling and reaming the hole. A good operator never allows a good tool to become dull. It is just as important to have the cutting edges ground properly on a core drill as on a reamer. This is best accomplished by machine grinding. For best cutting efficiency, the cutting chamfer of the tool must be concentric. The counterbore is essentially a reamer. Different size pilots can be used with each counterbore. Here, the operator is counterboring with a tool of this type. Several different pilot sizes can be used with each counterbore. In this case, the counterbore size on the next hole is the same as the one just completed, but the pilot hole size is different. So the operator just changes the pilot to fit this larger hole. This can be done more easily than changing the entire tool. Being able to use the same counterbore for many pilot sizes makes this a very economical tool. Many of the reamers which have been shown are also made with carbide tips. These are made by brazing carbide tips into hardened high-speed steel or hardened alloy steel reamer bodies. Carbide-tipped reamers have been successfully used for many applications. In certain applications, a hand reamer is required. The spiral-fluted expansion type, the straight-fluted expansion type, the adjustable type, the common hand reamer, and the taper pin reamer are 5 widely used hand reamers. The hand reamer is a simple, efficient tool. When assembling parts in a machine shop or on the assembly line, it often happens that one of the parts is not held to the proper tolerances. This condition can be corrected easily by the use of a hand reamer. The assembler can clamp the reamer in a vise and turn the part on the reamer until the necessary stock has been removed. It must be remembered that only light cuts should be made. Now that the hole size has been corrected, a good fit on the mating part is assured. In some cases, the part to be reamed is so large that it cannot be picked up. The assembler, however, should never use a monkey wrench to turn the reamer in the workpiece. If it's used, the reamer will wobble badly because there is no balance. This will result in a tapered and oversized hole. The proper procedure is for the assembler to use a tap wrench for turning the reamer. Use of the tap wrench provides better balance. Bad wobbling is eliminated, and the reamed hole will be accurate. In assembling parts, there often is considerable variation in the size of the male part. The expansion type hand reamer is a convenient and economical hand tool used to correct this condition. The reamer is expanded by turning the expansion pin. The hole then is reamed to the required size. Only a few thousand should be removed at one time. The hand expansion reamer thus has saved time and eliminated the necessity of having a large number of different size reamers on hand. The adjustable hand reamer is also a very economical tool. When the blades wear out, it is easy to replace them with another set, which is already finished ground and ready for use. Single blades should never be replaced, as the blades are furnished in matched sets. A simple adjustment is all that is necessary to increase or decrease the cutting diameter. Just a few adjustable reamers will permit the reaming of hundreds of hole sizes. Where taper pins are used in the assembly of machine parts, taper pin reamers must be used to secure proper fit. After the parts have been assembled and drilled, the holes then can be reamed with either a straight or spiral-fluted reamer. Both of these types are suitable for this purpose. After reaming, the proper sized taper pin is inserted and lightly driven in the hole. This properly locates and holds the parts together. For special jobs, special reamers are designed, such as these, which are made up particularly for mass production in order to combine various operations. These examples include the piloted reamer, the guided reamer, the line reamer, the step reamer, the taper reamer, and the combination drill and reamer. The combination drill and reamer is used to drill and ream a hole to size in one operation. Properly applied, this tool will produce satisfactory finish in the reamed hole. This cross-section shows the finish produced by the reamer portion of the tool. The step reamer is a tool in which two or more reamers are combined. It is used when two or more diameters are to be reamed. This tool is made up to accomplish this in a single operation. The piloted reamer is designed to be used where it is essential to pilot the reamer into the hole to be reamed. This may be required to secure either the necessary accuracy of location or the proper alignment between the holes. These special reamers consist of two parts, the reamer portion and the pilot. Occasionally, a special reamer with an unusual taper is required. This special tool is available in various types of flute construction to ream the hole to the desired taper. The guided reamer is essentially a piloted reamer, except that the guiding section, or pilot, follows the cutting section. It is made up for those jobs where the needed accuracy must be preserved, but where a piloted reamer cannot be used. A special line reamer is used where it is important that two holes be aligned. This tool combines into one reamer the features of both the piloted and guided reamers. The cutting portion of the line reamer is given greater support by the pilot on the one side and the guide on the other. Whether the holes are of the same size or of different sizes, this type of reamer will align them. Having become acquainted with the various types of reamers and the uses for which they are intended, the operator also must learn to use them properly. In production drilling and reaming operations, many factors must be considered. For example, operating speed and feed. The speed of drilling must be determined in relation to the kind of material being drilled. Also, the rate at which a drill is fed into such materials is important. In reaming operations, however, these speed and feed factors are changed. These can be readily determined from the proper drilling conditions for a given material. Reaming feed is often from 2 to 3 times the rate used in drilling in order to provide sufficient chip load for the reaming teeth. Reaming speed, however, is usually 1/2 to 2/3 that used for drilling the same material. If the reamer is run at too slow a feed, it will wear long before it should. This tool is cutting undersized after only a few holes have been reamed with it. With a new reamer installed in the machine, the feed is brought up to where it should be. When the proper feed is applied to the tool, each tooth will carry its share of the load. It will also ensure sufficient chip thickness to be removed and prevent excessive wear on the cutting teeth. This reamer then will cut many more pieces within tolerances. Another important factor in the use of reamers is the selection of the proper coolant. In drilling operations, a coolant is necessary to dissipate rapidly the large amount of heat that is generated. In reaming, the purpose of the coolant is to lubricate and assist the tool in securing the proper cutting action. This will give the best finish and accuracy in the hole and the longest tool life. In machines capable of doing both drilling and reaming, such as automatic screw machines and turret lathes, it is often necessary to compromise on the proper coolant to use. It is selected to suit both operations, or the one giving greater difficulty. Many materials are drilled best without any coolant. For reaming, however, it may be necessary to use a lubricant to secure proper hole size and finish. The amount of stock left for reaming is also of great importance. Although the proper amount of stock will vary for different types of materials, there are certain precautions which must be observed. For example, if too much stock is left, the reamer may be broken. Here's what happens. The hole is full of chips, and the reamer is wedged in. Just enough stock should be left so the reamer can have something to bite into. This will ensure a good finish and reduce reamer wear. If not enough stock is left for the reaming operation, the drill marks will be visible after reaming. This also causes excessive wear on the reamer. Chatter is one of the troublesome aspects of reaming. It may be caused by a number of things. Running at too high a speed, for example, will cause the tool to chatter. When chatter marks appear, the operator should first check his speed. He must stay low enough to eliminate this condition. If it isn't excessive speed, it may be lack of rigidity in the machine itself that is causing chatter. It may be lack of rigidity in the tool and spindle together. Or it may be lack of rigidity in the work-holding fixture. Chatter is generally an indication that the tool does not have sufficiently rigid support. It cannot withstand the forces to which it is subjected. Chatter also may be caused by the excessive clearance that was ground on the reamer. Excessive clearance on either the chamfer or the outside diameter can be very troublesome. This condition makes the tool cut too freely. It often results in the tool cutting ahead of the feed being applied to it. Any one of these conditions may result in a surface showing chatter marks. Thus, to eliminate chatter, the operator may have to correct several things. He must replace the reamer that has the excessive clearance with one that is ground correctly. He must shorten up overhang of the tool. He must make the machine more rigid by tightening gibs and securely locking the table. he must increase the rigidity of the work-holding fixture and securely clamp the workpiece in the fixture. He must reduce the running speed of his machine. Now that all the factors tending to cause chatter have been corrected, the operator can resume the reaming operation. The result is a well-reamed hole without chatter marks. Another frequent problem encountered in reaming is that of eliminating out-of-round or bell-mouth holes. This condition is generally caused by misalignment between the spindle axis and reamer axis. This is an example of an ideal condition of alignment, with the spindle axis and reamer axis coinciding. This condition, however, is rarely, if ever, obtained. We assume, therefore, that this ideal condition does not exist. Misalignment is of two distinct types. One of these is known as parallel misalignment. In parallel misalignment, the reamer axis is parallel to the spindle axis, but is lower in position. The second type is known as angular misalignment. In angular misalignment, the shank of the reamer is in line with the spindle. The reamer, however, has been clamped or positioned at a slight angle. This angular displacement can be in any direction. In actual practice, both of these misalignment errors usually are present at the same time in a single setup. This can be caused by a combination of several factors. Among them might be improper leveling of machines, improper location or adjustment of tool slides, or errors in indexing mechanisms. Other contributing factors are worn ways or loose turret mounts on machines. Worn or dirty sleeves, and worn or dirty holes in the tool holders. Here's a reamer rigidly held at an angle to the spindle of the machine. Let's see what happens when this condition of misalignment exists. As it is fed into the work, the lower flute will bear harder and harder against the wall of the reamed hole at point A. The pressure built up against this flute results in a scraping action at this point. The hole thus produced is either oversized or bell mouth, as shown in this cross-section. This can be recognized by the gouges and tears in the front portion of the reamed hole. Some of the conditions causing these difficulties can be easily corrected. Loose ways, for example, can be tightened. Dirty tool holders can be cleaned. And worn sleeves and bushings can be replaced. Other corrective measures require more time and expense. Additional correction can be made. Care in the selection of the proper type of floating holder is essential, since some types correct for either angular or parallel misalignment only. Other types of floating holders can correct for both types of misalignment. These permit a full float in all directions. The type of construction used in the manufacture of full floating holders will generally provide a means of reducing any tendency of the tool shuttering when being used. Other corrective methods possible are through the use of adjustable holders. This type of holder permits the reamer to be moved into exact alignment. It is then clamped in that position. It will then need no further adjustment until the setup is changed or the reamer is removed for regrinding. The use of these various types of floating holders is the most common method employed to overcome the condition of parallel or angular misalignment. Sometimes it may be necessary to rebore blank bushings in the turret in line with the spindle axis. Still another method for eliminating a bell mouth condition is to remove that part of the flute which interferes. This is accomplished by regrinding the reamer with a back taper. In the interest of tool economy, back taper should be kept to a minimum, as the tool will lose size rapidly on successive regrinds. Another reaming problem frequently encountered is that of obtaining a straight hole. This difficulty is particularly troublesome in the reaming of holes of considerable depth. Difficulty in passing a straight rod through the piece is due to a bent hole condition. Instead of using a reamer of conventional grind, such as this one, for the reaming operation, the condition can be remedied by using a roughing reamer, like this one, which has been ground and cleared like an end mill. It has sharp 90-degree corners. A reamer ground in this manner is not influenced by the shape of the original hole, but will cut its own true path. After the hole has been rough reamed with a tool of this type, it can be finished reamed with tools having conventional grind. A method of grinding, such as used on this one, will give the necessary size and finish. Occasionally, a short, relatively flat secondary angle or entering taper can be added to this type of grind. The addition of this entering taper will ensure the reamers following the previously established straight hole. It may also improve the finish of the reamed hole. Now that the hole has been straightened and finished reamed, the rod will pass through it without any difficulty. Holes that are off-center should never be reamed without a bushing, because the reamer will bend as it tries to find the hole. Installation of a bushing plate will permit use of a bushing. The hole then will be located in the right position. Bushings that are worn and oversized, however, cannot do a proper job. Therefore, a regular check should be made of the bushings that are being used. It is important that the spindle be lined up accurately with the bushing. Proper lineup and good fit will help ream accurate holes. One of the most common causes of reamer wear is the excessive heat generated by dull cutting edges. Such heat causes a rapid breakdown of the cutting edges. The use of tools in such conditions results in poor reamed hole finishes. This situation, however, can be avoided very easily. The solution, of course, as with any other cutting tool, is to resharpen a reamer long before it fails to do a good cutting job. This operator, for example, has made too many pieces without regrinding the reamer. Let's see what actually has happened to the originally sharp cutting edges of this reamer. The first indication of reamer wear was a rounding of the sharp corner. Continued use of this dull tool then produced a front taper. To restore the tool to its former cutting efficiency, both the rounded corners and the front taper must be removed. Consequently, when this reamer is sent back for resharpening, extensive corrective grinding will be required. This means that most of the tool will have to be ground away to get a satisfactory cutting edge. This is how a reamer might look after the extensive corrective grinding required by its badly worn condition. In production reaming, this condition can be avoided or materially reduced. To accomplish this, the job should be set up on a predetermined holes per grind basis. If this practice is established, it will avoid any unnecessary abuse of reamers through excessive use. Thus, the operator will not run the risk of producing pieces which would be undersized or have poor reamed hole finish. It will also ensure the removal of tools for regrinding after the proper number of holes have been reamed. Although this operator has produced fewer pieces per grind, the reamer that was used should be removed for regrinding. Therefore, when this tool is sent back to be reground, much more of the usable part of the tool will be left. Note how little stock was removed from this reamer to restore its cutting edge. Accurate regrinding, of course, is of the greatest importance in proper reamer care. Most regrinding is restricted to resharpening of the cutting chamfer. Sufficient stock must be removed to eliminate any worn or scored surface on the chamfer or land. Here is a reamer before regrinding. This is how it looks after regrinding. In addition, proper clearance must be provided to prevent the heel of the chamfer from rubbing in the hole. The amount of clearance is best checked between centers and measured in indicator drops. The amount of clearance to be ground will depend on the size of the reamer and the material being cut. Most resharpening can be done on any commercial tool and cutter grinder. After placing the reamer between centers in the grinder, the locating finger is set to provide proper clearance on the chamfer. The face of the flute is held against the locating finger by light, steady hand pressure. The choice of the kind of wheel to use is up to the grinder and the type of equipment he has available. One man will use a cup wheel. Another man will prefer grinding on the periphery of a straight wheel. In either case, the wheel is rotated to grind into the cutting edge. It is important that the setup be as rigid and compact as possible, with a minimum amount of overhang. Some men, therefore, prefer to support the body of the reamer in a bushing. This method is used when the center of the reamer has been destroyed through repeated regrinding. Whatever the method, a rigid setup and application of uniform pressure should result in a chamfer concentric with the reamer body. Concentricity, however, should never be left to chance. It must be checked. A common method of checking is through the use of bench centers and dial indicators. The reamer is mounted between centers, and the indicator is adjusted so that the axis of the indicator is perpendicular to the chamfer, and the indicator anvil is under light tension. The reamer then is slowly revolved to obtain the maximum reading on each cutting chamfer. Another method commonly used to check for concentricity involves the use of a contour projector. With this equipment, the form of the cutting edge is projected into a luminous viewing screen. The base, or measuring line, is lined up with the cutting edge, and the reamer is slowly revolved, pausing slightly as the image of each cutting edge is brought into focus. The relative position of the shadow with respect to the original line shows the chamfer run-out. This method has the advantage of also showing any errors in the chamfer angle between cutting edges. Note the variation on this tool. Here is one method of regrinding a reamer that is never recommended. When grinding by hand, it is impossible to get the chamfer even. Putting this hand-ground reamer in the contour projector will show exactly how well it was ground. Note the variation in the length and angle of the cutting edges. Reamers in this condition would never have a chance to produce smooth, accurate holes. Proper grinding is vital to the reamer's efficiency. But what's the use of careful grinding if the reamers are carelessly handled and stored like this? No matter how carefully the reamers are stored in the tool room, they are often abused in handling by the operator. Carelessness such as this can only hurt the tools. If these reamers are examined closely, they probably will be found to be damaged. See that nick? It was just made by the operator's mishandling. Later, he'll wonder why he can't get a good hole. There's one right way to handle reamers. They should be in containers when taken away from the tool crib. At the workbench, they should be handled carefully and kept apart from each other. Treatment like this will pay big dividends in smooth, accurate holes and long tool life. Careless treatment of reamers is reflected in other ways, too. Among other factors that cause unnecessary damage to reamers is a loose or worn spindle in the machine. Other damage is done by tapping the reamer with a hard hammer rather than a soft one made of babbitt, bronze, copper, or rawhide. A soft hammer will prevent damage of this type. Worn or dirty sockets will cause damage by making reamers wobble in their sockets or run out in them. This is the kind of care they should receive. Reamers are precision tools. They must be stored properly. Any method which prevents them from banging against each other is all right. There are a number of good ways to store them. In drawers is one way. In cubby holes is another. They may be stored in individual compartments. They also may be placed in stands. Additional precautions can be taken in storing reamers. For example, reamers are often placed in pasteboard cubes or pasteboard boxes. They may be stored in plastic containers. Keeping them in canvas bags is another method. While some tool rooms prefer to dip them in a plastic protective coating material. All these methods are good tool room practice. Thus, the reamer serves faithfully in the countless industrial applications requiring holes to be held to close tolerances. No matter what the reaming problem may be, one requiring simple hand reaming, or the heavy-duty reaming of structural steel units. A reamer exists or can be created that will reduce or eliminate the reaming problem. Respected as a precision tool, properly used and properly cared for, the reamer is available to meet all industrial demands for holes requiring better finish and greater accuracy of size and location. Where precision is the watchword, the reamer is there to serve.